Okay, so this is be our last recorded lecture, last class this semester on this course. In the past two lectures, I've explained how you can go from data to extract flexibility matrices in sensor coordinates, and how the changes in that flexibility matrix can be utilized to localize damage in structures. Now, today we will conclude by presenting a generalization of that approach, which is called the dynamic damage locating vector approach. The DLV, or damage locating vector approach, is the original formulation which it works with changes in flexibility. In the dynamic version, the DLV, we operate with changes in the transfer matrix. Now, the flexibility is the transfer matrix at evaluating the Laplace domain at S equal to 0. So this is basically an extension, or, well, it depends how you want to see it. You can see that what we've done before is a special case, perhaps, of what we are going to do now, which is to locate damage from the changes in the transfer matrix. Now, the computation of the transfer matrices from data I've already covered in the previous class, right? I particularized it at the end to flexibility by putting S equal to 0. But by evaluating it at an arbitrary value of S in the complex plane, then you would have the transfer matrix at that value of S, okay? Now, why do we need another method? Why not just stick to the one on the flexibility? Well, evaluation at S equal to 0 has certain advantages in the sense that the uncertainties that there may be regarding the mass of the structure, right, does not play any role. The uncertainties that there may be with regards to the damping of the structure do not play any role in the method itself. That is, we compute the flexibility from the data, and then, since the flexibility only depends on stiffness properties, damping and mass properties do not enter the problem. The price that is paid for that, however, is that the resolution with which we can identify damage is limited to the resolution that can be obtained in a static analysis of the structure, okay? Consider, for example, the situation of a shear building like this, where we have, let's say, sensors here, sensor here, and sensor here, right? Let's say we have 3 sensors. When we calculate the flexibility matrix, let's say, assuming that we also had, we are able to expand it to those coordinates. Here is the input, right? And here is the output. We would get a flexibility which is 3 by 3 connecting inputs to outputs at these locations after we expand, as explained last time. But once it's all said and done, and we calculate the changes in the flexibility, and then from the changes in the flexibility we calculate the null space and the damage locating vectors, then we will get things. Let's say that the damage was here. Then that means that a damage locating vector is such that it must have 0 shear here, right? Because this is a shear building and that's the stress field that matters. So, for example, this could have been 10, that could have been 2, and that could have been 12, right? In which case, the shear flow would have been 10, or the pattern, would have been 10, then going to 12, then going to 0, and like this, right? So, using flexibility, because we had sensors here, it becomes impossible to differentiate between this level and this level, right? All we can say is that there is no damage in this part, but we cannot really specify what the issue is here, because we are using just static loads. When we apply the dynamic version of the method, as you will see, we no longer have the limitation of statics, because we are using also excitation that arises from the inertia of the structure, and so we will be able to find further refinement on the position of the damage. Another advantage is that we can aggregate results at different values of the Laplace variable, right? The flexibility matrix is the transfer matrix evaluated at S equal to 0. But the transfer matrix is a matrix that is parameterized on S, and so you can evaluate the transfer matrix at many different S values. And as we will see, we can take information from many of these different S values and join them together in an aggregate form to gain additional confidence on the nature of our answer with regards to where the damage is located. Okay? So let's begin by presenting the fundamental equations of the derivation of the dynamic damage locating vector scheme. Okay? We begin, let's say, with the equations of motion, mq double dot plus c damping q dot plus the stiffness q is equal, sometimes I write this as B2ft. In this case today I'm just going to call it ft, the load from the right side, right? Now let's assume that the structure gets damaged and that the damage is restricted to being changes in the stiffness. It doesn't have to be, but that's the 99% of the times what we are interested in. So let's assume that the mass remains the same, and in the damage state there is another response. I'm going to use a bar to refer to the damage coordinates, to the damage response. The damping we assume has not changed, and so we have this. But let's say that we think the stiffness has changed, and we express the new stiffness as the original one plus some change. And so we have this, and then there is some other loading, let's say, right, that we've applied. So basically this is just simply a statement of, this is the equations of motion when the structure is in the healthy state for some loading. This is the equations of motion when the structure is in the damaged state for some other loading, right? Now let's require that the loading be the same. So let's say that F and F bar T are equal. So we're going to apply the same load. Well, that's easy, right? I just simply say my experiment was done like this, and this is with the same load. Well, I shouldn't say that's easy from a point of view of an experiment, because we're actually not going to do that, but we're not going to be applying any loads like this. But in the derivation, it's clear that I can say, let me see what happens if Ft is equal to Ft bar. And also, I want to put the requirement that Q be the same as Q bar. Now that's a little bit more subtle, right? We're saying I want the structure in the healthy state with a load Ft, and the structure in the damaged state with the same load, okay, but a different stiffness, to have the same response. If that is to be true, then what has to happen? Well, if you now change this Q bar to just Q, or this one to Q bar, whichever way you want, and subtract the two equations, you can see that the inertial term cancels, the damping terms cancel. Here we get something like this, delta K times, I could call it Q or Q bar, but let me just call it delta K Q must be 0, right? Because the right side we set the same. So if this is to be possible, then this must be true, right? So our stiffness matrix multiplied times the response must be 0. Let's say that we distinguish that response by referring to it as being, I don't know, Q double bar. Okay, so Q double bar is the response that exists when these two things are made identical. Now, mathematically this tells us that Q double bar is always in the null space of the change in the stiffness matrix, right? The change in the stiffness matrix therefore must be rank deficient, right? Because if this was full rank, there would not be the possibility of having vectors that times delta k were 0. By definition, a matrix can be multiplied by something and get 0 only if it's rank deficient, right? So delta k, that is the change in the stiffness due to the damage, must be a rank deficient matrix for this to be possible, okay? Now, let's see. There is, I will give you the reference later, but in the original paper, at this point, there is a section in which we explain or derive that if this is true, then that means that this loading is producing no stresses over the part of the structure that has suffered the damage. Okay, so let me write that. It can be shown that the response Q double bar T, that is the response for which the system in the healthy state and in the damaged state is the same response, even though this matrix is different and its loads are different, that the response is such that sigma T in the damaged region is identically 0. That means if there is any part of the domain, this to do it in general, let's say this is the structure, right? And let's say this part over here is where the damage was located. Then in this region, the stress field for all time that the response is Q double dot is identically 0. Okay? So what we seek to do in the DDLV approach is to determine what are the loads on this side, right? What are the loads F T double bar, if you'd like, for which this is true. Notice that in this derivation here, what I said simply is that they were equal. I didn't say what it was, right? They are equal. If these loads are equal and the response is equal, then this must be true. If this is true, delta K must be rank deficient. And then a proof shows that if delta K is rank deficient, I'm sorry, that if this load, that if this displacement satisfy both equations simultaneously, then with the same load on the right hand side, then that's because over the damaged portion of the structure there is no stress during the response. We do not know at this point really what are these loads on the right side, right? We don't even know if they exist. We're just simply saying if they existed, then this would be true. So the task of the DDLV method, and I'm jumping ahead all the way basically to the end, the task that we set out is the following. What are these loads? What is the load FT? And more importantly, what is it and how can I find it from the data, right? If I can find the load FT from the data, then I would be able to take the load FT, F double bar, meaning the correct one. I could apply it to my domain and find the stress field and then simply look for the region where it is 0. Okay, there's going to be, let's see, there's one subtlety, no, not subtlety, there is one detail that I must mention, which is that because we are in a system identification framework, I must restrict that these loads that we're looking for cannot be just any loads applied anywhere, but that they must be loads that act exclusively at locations where there are sensors, because otherwise I have no hope of being able to find them from data. Okay? This will become, let's see, more clear if I write something down. So I'll erase here. And say that my load the loads Ft double bar, let's say, that produce these two things to be equal, must be such that they have that, assuming that these are the measured coordinates, or coordinates where there are going to be sensors, and these are not measured, right? So there may be some loads here that produce identical response on the undamaged and damaged state, but they are acting at every coordinate. Those are not useful for damage location because I cannot compute them from the data. Okay, my structure, which is here, has sensors at some locations, maybe here, here, and here, let's say. So I have a sensor, and a sensor. We are looking for loads which are, in this case, they're going to be dynamic loads, but dynamic loads acting at these three locations, okay? Let's say, well, I don't have to know where the damage was, but I'm looking for loads at these three locations which will produce exactly the same response everywhere, right? In the healthy and in the damaged state, but I am looking for only loads that are applied where my sensors are. If I find, no, not find because I can't find them, but if I were to say that this loading produces identical response in the damaged and in the undamaged state, I am not interested in that loading because that loading has contributions at locations where I don't have sensors. So I will never be able to find what those loads are by processing data. Okay? I am only interested in the subset of the possible loads that produce identical response where the loads are non-zero over the measured coordinates. Now, for convenience in the discussion, if you want, you can think in terms of this vector q, if you'd like. It's not really necessary when one programs or when one executes, but if you'd like, you can think in terms of the fact that q has been partitioned into the measured and the unmeasured coordinates in that order. One can always think this way. That means then that when we calculate the f's, it is the first partition that is non-zero and the second partition is 0. Okay? In reality, I don't really need to reorganize when it comes down to actually applying the technique. And I think it'll be obvious when we look at the equations and so on. But for the purpose of the derivation, it's, you may want to think in this terms. So just imagine that my mass, my damping, and my stiffness matrices here are so organized so that the Q is the Q measured and the Q unmeasured. Okay? So that's it. Now, what we had was that delta K times the Q, right? Double dot as a function of time, must be 0. That was the requirement that we found from inspecting these two things. Okay, so if that is true, then here. So we have that delta K, the change in the stiffness matrix due to the damage, times Q double bar T is 0. We don't know this Q double bar T, right? In fact, we don't know anything. We're just simply laying out the mathematical constraints, see if we can learn something from it. So we have change in stiffness times Q double bar equal to 0. So now, from an understanding of linear algebra, we can say that Q double bar T must be the null space of delta K multiplied times an arbitrary function gt, okay? Where Q is the null space of delta K. That is, Q is, for those that are not as familiar with these concepts, if my matrix delta K was this, right, and I take this vector ABC, and that vector gives 0, then that vector is in the null space of delta K, right? And if that vector is in the null space of delta K, then that vector is part of Q, okay? So let's say that I say that that vector is ABC. Now imagine that I can also find that there is another vector, and that this other vector is XYZ, and that XYZ times this is also 0, right? Well, then the vector XYZ is also in the null space. Now here I'm treating it like if it was a 3 by 3. Now you could say, wait a minute, I can think of another one that works, the vector n1, n2, n3, and it's also 0, right? Well, yes, true, but if n1, n2, and n3 is a linear combination of these two vectors, then that's not a new component of the null space, right? Because n1, n2, and 3 is already in this subspace. And it turns out that if this matrix is a 3 by 3, and it has a null space of dimension 2, its rank would be 1, right? It only has a singular value that is non-zero, one of the 3, right? This delta K, if you were to break it into a singular value decomposition, it would have been something like this, and then something here like that, and there would be an S1, and then it would be 0 and 0, and then something here again, right? So there would be 2 zero singular values, indicating that the null space is of dimension 2. And this could be a basis for the null space. That's what I'm calling here Q. So what we're saying here is that during the response of the structure, this QT, right, could be, let's say, you know, this, well, let me use numbers. Let's say A, B, C, D, E, F, G, H, I, L, M, N, X1, X2, X3, Y5, Y6, Y7. And I could go on and on and on and on, right? This is time running that way. And these are different time stations. So I could have 10,000, right? I could have 10,000 of these, because I can solve for the response, let's say, for as long time as necessary. What we are saying is that any one of these vectors, A, B, C, or Y5, Y6, Y7, all of them, right, are actually such that when multiplied times delta K is 0. Therefore, they are all in the null space of delta K, so they are all linear combinations of the columns of Q. Okay? These vectors are all linear combinations of the columns of Q. Right? So if Q here had two columns, let's say the column C1 and the column C2, then any one of these things, like that one, for example, x1, x2, and x3, is simply equal to the column 1 times something plus the column 2 times something else, right? And that would apply for any one of the vectors. Therefore, the vector g here, in this particular case, would have two numbers, and those would be the alpha and the betas that are combined in the columns, right? Okay. So, with Q being the null space of delta K, we can write Q double bar as QGT. We can then go back to the equation of motion and write M, and then instead of Q double bar, double dot, we can just say Q times G double bar, G double dot of T, right? Plus C dam times Q times G dot of T. Let me see, which notation did I use here? Okay, plus K, I'm going to the original one, right? Times Q, I could do the K plus delta K, it doesn't matter because this has to apply in both equations, right? Times G of T. And that is the first equation, right? Well, actually, not the first equation. This is the case of the system. And I said that this is the load, right? Now, we've said that we're only interested in loads which are not zero over the measured coordinates. So these loads that are on the right-hand side that I am trying to find would have to satisfy this equation, right? The response is Q times GT. It's been substituted back, and I am not interested in the general case. I'm only interested in the case where this partition is zero. Now, in order to make the left side compatible with the right side, I'm going to write this product as a matrix like this and call the upper partition EQ and the bottom partition EU. So this is that times G double dot T plus C dam times Q. Let's write it also as a double partition of, let's say, FQ and FU. That's times G dot T plus K times Q. Let's say we write it as the partition NQ and NU. And that goes times GT. And then that is equal to our LT and 0, right? Okay. That's equal to LT and 0. Now, let me erase here. Okay, so let's see. What is the size of Q? Maybe I should have done that before, but anyway, what is the size of Q? The size of Q is the null space of delta K, right? Delta K is an N, let's say we call N the number of degrees of freedom. So delta K is an N by N matrix, right? Let's say that the rank of delta K is, what do I call it, P or Q? P. So let's say that the rank of delta K is P, okay? So if the rank of delta K is P, then Q is a matrix, right, that must have N entries like this, and in this direction is equal to N minus P, right? Why am I saying N minus Q? Just a second here. Yeah, Q is N minus P by N, right? So this is the null space of delta K. Now, when we multiplied any one of these matrices, for example, the matrix M times the matrix Q, we were multiplying a matrix that was N by N, right, times the null space matrix, which was N by Q, by N minus P, I'm sorry. So what we got as an output was at N minus P by N, right? So this whole thing is N minus P this way by N this way, right? And therefore this partition here, which is Q coordinates, right? Those are the measured ones. This partition here must be N minus Q. All right? So all these matrices are Q by N minus Q, Q by N minus P, and here N minus Q by N minus P, right? Okay. So I erase here and continue with our derivation. So we have this, right? These are M times Q. Notice that none of this matrix we ever had, right? Because in order to actually compute this matrices, I would have to have the delta K. And if I had the delta K, to get the null space and so on, I don't need to solve the problem because I already know the damage. That was the delta K. So this is all done in order to derive some result that eventually becomes useful, but not because we can explicitly compute any of them, right? So now if we look at the second partition, we see that for this to be possible, for this equation to be possible, EU times G double dot T plus FU times G dot T plus NU times GT must be identically 0, right? Now the matrix, all these matrices have the dimension N minus Q, N minus P. Now, if these matrices are squared, then this is a polynomial eigenvalue problem, right? Because it's squared, 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 it's called a polynomial eigenvalue problem and it has a solution. If these matrices are wide, okay? If these matrices are wide, then there are infinite solutions. It's easy to solve, right? If it's wide, there are infinite solutions. If it's square, the solutions are always of a particular form. Let me see if I wrote it down. No, I didn't. But I think these solutions are of the form, are a special form, something like, it'll be something like GT is equal to something like G0 e to the ZT or something like that, right? It's a decaying exponential kind of solution. If the matrix is not important for us here, right now, and if the matrix is tall, that is, if this is like this, then in general there's no solution. Okay? So right now, by looking at this, we are saying, in our attempt to derive these loads that produce identical response and therefore zero stress over the damaged region, I have found myself under a constraint here. And that is that in order for them not to exist in general, but to exist and be zero in the part that I'm not measuring, then I must be either squared or this. So let's look at the square case as the limit. Therefore, n minus q, right, in the square case is equal to n minus p, right? Or I should say not equal. We are saying y means n minus p, n minus q must be smaller or equal than n minus p, right? N minus q, that is, this should be small compared to n minus p. So, subtracting n from both sides and multiplying by minus 1, which reverses the inequality, we get that q must be greater or equal to p, right? What does that mean? What is p? P is the rank of delta k, right? And q is what? Number of measurements. So from here we conclude that in order to be able to locate damage using our approach, which we are attempting to develop, for loads that produce the same response everywhere and therefore zero stress over the damage region, and are zero in any coordinate that we are not measuring, then the number of measurements must be greater than or equal than the rank of the damage. Okay? Now, the rank of delta K depends on the type of structure, okay? So if you have in a shear building, for example, okay, each floor damage, or no, not each floor damage, I can just say the rank of delta K in a shear building, the rank of delta K is equal to the number of floors damaged. That you can easily confirm, right? You can just simply calculate delta K and show yourself that that is true. In the case of a truss like this, for example, right? If you have damage, let's say on this bar, and that bar or something, right? And you say, what is the rank of delta K? Then the rank of delta K is equal to the number of damaged bars in general. So in this case, it's easy to count, right? If you go now to a more complex situation, let's say this is a plate. Okay? Now a plate is a continuum, and in a continuum we have problems because the equation is not the equations of motion are partial differential equations. So we're going to replace the plate, let's say, by a finite element model, right? So let's say that our plate has been replaced by some sort of a finite element model approximation, okay? Now, our finite element model maybe are triangles, so if I go like this, I can think that I have a finite element model made by triangles. Okay? I may have messed it up, but it doesn't matter. If you now look at one of them, let's say this finite element, right? Let's say that the damage took place on that element. Then if you look at that element by itself, okay, we can say how many degrees of freedom does that finite element have? Well, if the plate is in this plane, we would typically assign in a model of the stiffness 3 degrees of freedom per node. That is, we would have the displacement perpendicular to the plane as being one coordinate, plus the rotations about these two axes, right? We can rotate like this. We can rotate about this, and we can have in and out of the plane. So there would be 3 degrees of freedom per node, so there would be 9 degrees of freedom, right? Now, the rank of delta K, if I got damage over one of these plates, would be the number of degrees of freedom in the element minus the number of rigid body modes. That is, how many ways can this element move without incurring any strains. And in this case, we would find that the number of rigid body modes would be 3. So the rank of delta K would be 6 if we had damage over one element. This generalizes the idea to say simply that when we have a model, because this is all model connected, right? If we have a model of a structure and an element on that structure suffers damage, meaning we change its properties, how much is the change in the rank, what is the rank of the change in the stiffness? We can say in general that the change in the rank of the change in the stiffness is the sum of the degrees of freedom associated with this element minus the number of rigid body modes that each one of these elements have. Okay? If you look at the plate, for example, and we already said that Q has to be greater than P, so if we wanted to detect damage on this element, theoretically, we would need to have at least 6 sensors, right, on this plate. In reality, what that means really is that in order for the theory to apply exactly, that is, to have a perfect null space, you need to have 7 sensors or 6 sensors, right? In practice, although we don't have time in this class to go into this level of detail, but when you actually try it, what you find is that you can often get very useful results by using quasi-null spaces, that is, null spaces that are not exactly associated, not null spaces, but portions of the singular value decomposition that are not associated with exactly 0 singular values, just simply with sufficiently small singular values, okay? So I will not dwell much further, but just to say that in the case of shear buildings, okay, which we normally are using here to illustrate our things, in the case of shear buildings, the rank of delta K is the number of floor damage. So if we had one floor damage, we would need at least one sensor, preferably 2, so we have several solutions that are not just the decaying one. And you know, if we had 2 damages, we would require 3. Okay, let's say we take the one of having 1 plus the number of damage locations. Okay, so I'm going to stop the recording now to create the second part for controlling the length.